Okay, well, happy Friday, happy week 9 Friday. We have just 1 week left in the class because I'm giving the final on 10th week Friday, and so yeah, so we're almost there. On Monday, so I haven't written the final yet. I'm still kind of working on it, and I'll provide more details on Monday. I think as far as Monday's lecture goes, it will be something light and, as far as Monday and Wednesday's lectures go, I will not test you on that material. Okay, so I won't test you on Monday and Wednesday stuff. I'll try to find stuff that's interesting to me, and hopefully kind of interesting to you guys. I don't know, but I won't test you on it. So this will be kind of the last lecture for material, and yeah, we'll go from there. Student last class asked if I'm going to have a review session. I do not plan on having a review session, but I'll have kind of my regular office hours. I'll cancel my Friday office hours, and I'll reschedule my Friday office hours to some other time during the week. And so that's what we'll do. Okay. All right. Let's take a look at Bootstrap with library boot today. Okay. And so this lecture, I'm going to cover this, or at least introduce package boot. And so this library is has been around for a while, and it is it's, I would say, the library that people use when performing Bootstrap in R. Okay. And so, pretty much all the examples I did in Wednesday's lecture were all kind of, I just wrote loops myself, and we calculated values and we stored them somewhere, and we went off of that. And library boot pretty much does similar functionality as far as doing Bootstrap replicates and resampling. But there are functions built around the results, because it outputs a data structure that we can then use. Okay, so if you look, if you install, so you're going to have to install packages boot if it's not already on your computer. It might already be there, and you might be able to just type in library boot. But if you look up the help file, the documentation for boot, which is pretty much the primary function that you use, this is what it'll say. So I just copy and pasted this from the documentation, and it says generate R Bootstrap replicates. That R here is a number. Okay, it's this number. It's so generally like something like 10,000 or 100,000 or some big number. Okay, generate R Bootstrap replicates of a statistic applied to data. Both parametric and non-parametric resampling are possible. For the non-parametric Bootstrap, possible resampling methods are the ordinary Bootstrap, the balanced Bootstrap, antithetic resampling, and permutation. I have no idea what some of this stuff is. Antithetic resampling, I don't know. And even though it says both parametric and non-parametric resampling are possible, at least for this lecture, I'm only going to cover non-parametric Bootstrap. Okay, again, in non-parametric Bootstrap is where we assume our sample is representative of the population. And so to kind of create our population, we're going to just make infinite duplicates of the current sample that we have and say that this is then going to represent the population. We draw samples, but of course we don't actually have to create infinite duplicates. We can just sample with replacement, and that's mathematically equivalent as creating infinite duplicates of our population. The during office hours, a good question about kind of when we use parametric Bootstrap and things like that. And pretty much the time you would use parametric Bootstrap is in situations where you would be willing to do a parametric test, like the t-test or chi-squared test or something like that, where you're effectively making assumptions about the distributional nature of the sampling distribution. It's just that maybe it's a situation where you don't, maybe the math gets a little bit weird, such as, what's the sampling distribution of the 10th largest value in your sample. This sampling distribution might be a little bit challenging to figure out, and so parametric Bootstrap can kind of solve your problems there. But again, in those situations, you're making parametric assumptions about the population, which is often an okay thing to do if you can justify your reasoning. Okay, but again, for non-parametric Bootstrap, we're not making parametric assumptions. We're just assuming our sample of data is representative, and we'll just take a look at the ordinary Bootstrap. I guess you can look up some of this other stuff here. Okay, if you do have multi-sample problems, then you can do stratified resampling. All right, and so that would be kind of a vector of strata to kind of make sure that each strata is appropriately represented. Okay, so I don't know if you had samples that were taken across the US, maybe you want to make sure each region, like the West and the East and the South and the Midwest and things like that, are all kind of represented appropriately in their respective proportions, and it can be done that way. Other things can be done. If you look at the call, the usage call, you'll notice these three arguments, data, statistic, R, don't have default values, whereas everything else does have a default value specified. So I'm really only going to take a look at these three, and I'm just going to assume that you are going to use the default arguments for the other cases, right? Bootstrap is one of those processes where you can run parallelization if you've got if you're doing many replicates, and so that's basically, instead of having one person doing 10,000, you can split it up in kind of a multi-core system. Like your computer might have several cores, and you can say, well, instead of one person doing all 10,000, one core doing all 10,000, it can split it up and say, all right, you got 4 cores, each of you do 2,500 running simultaneously in parallel, and the calculations can get done a little bit faster and things like that. So it often requires a little bit of back-end work to get set up. For a lot of things, at least the examples I'm doing here, they're simple enough where it's not a dramatic difference between these things, but certainly for more complicated ones, that might be something you want to do. Okay, so as far as these 3 arguments that we need to pass, we're going to have to pass the data. Okay, the data could be a vector, a matrix, or a data frame. And if it's a matrix or data frame, then it's expecting your data to be in tidy form, right? Each row is going to be considered to be one multivariate observation. So every row is an observation, every column is a variable. And so, we're kind of already assuming your data is tidy, and so Boot expects your data to be tidy as well. And then R is the number of Bootstrap replicates. So this is going to be some positive integer, something like 10,000, maybe 5,000 or 100,000, depending on how many values you want to do, right? As far as the statistic is a function, okay? It's going to be a function that we have to write, and when applied to the data, it's going to return a vector containing the statistic or statistics of interest. So, the examples that I'm going to look at today will just return one statistic of interest, but you could set it up to return multiple statistics of interest. If you want the largest value and this, 10th largest value or something like that, you can set up your vector or your function to return a vector of a length longer than 1, okay? The statistic function must take at least 2 arguments. The first argument passed will always be the original data, and then the second will be a vector of indices, frequencies, or weights, which define the Bootstrap sample. And so we'll take a closer look at that. All right, and so function boot again requires the data that's going to be resampled, the statistic to be calculated, which is a function we define, and the number of replicates R. Everything else has default values. So, so I'm not going to delve too much into it. Okay, the way the function boot performs the resampling is that it resamples the indices. Okay, it doesn't resample the values in your data directly, but it resamples indices, and it uses those indices to then subset the original data. And then after it subsets the original data, then you can calculate statistics based on the subset data, the resampled data in that way. And so I'm going to kind of illustrate how this works. And I'm going to just start off with a very simple toy example. And I think over here I said on the next 2 slides, but I kind of reduced it down to 1 slide here. Okay. So we're going to pretend our population is going to be the 26 letters of the alphabet, right? So we're going to just say our population is A through Z. And what I want to do is I want to produce a sample of 10 letters, okay? And so again, my population is going to be the letters A through Z, and I'm going to kind of duplicate this infinitely many times. So I've got, the letters A through Z all show up with equal proportion, and instead of actually having to duplicate it infinitely many times, I can just sample with replacement. So I'm going to take the letters vector and set it as my population. I'm going to set a seed here. And what I'm going to say is I want to get 10 letters from the population with replacement. Okay, so I'm going to say replacement true. We're going to sample 10 letters from the population. And the letters I get are B, K, Y, O, K, Y, I, U, G, W. Okay, and so just by kind of coincidence, from resampling, I selected the letter K twice and the letter Y twice. And also just by coincidence, they kind of came in together, KY and KY over here. That's just a coincidence, but it could happen, right? You could imagine, the letters tumbling around in, I don't know, like a bingo machine, and then you just draw one letter out, you get the K, letter K, you throw it back in, you get the letter Y, you throw it back in, and then later on, as you're drawing letters, you get the K again, and that something like that could happen, right? So this here, I sampled the letters directly from the population. I've sampled the values. Okay. Now I'm going to do pretty much the same thing, except I'm going to do it by sampling indexes. All right. So instead of sampling the letters directly, I'm going to create the vector 1 through 26, which is going to be the numbers to represent my index of letters. Okay. And then I'm going to sample those numbers 1 through 26, the indexes, with replacement. Okay. So I'm going to do sample 1 through 26. I want 10 numbers drawn from 1 through 26 with replace equal to true. And if I use the same starting seed, set seed 5, I'm going to get the same results. Okay, I'm going to get 2, 11, 25, 15, 11, 25, 9, 21, 7, 23. So the 2 corresponds to B, the second letter in the alphabet. The 11 is the K. All right, so I get the K here. 25th letters is Y. And then 15 is O, 11 again is K, and 25 is Y, right? And so these 2 methods yield the exact same results, okay? I can either sample the letters or the values in my population directly, or I can sample the indexes 1 through 26, and then basically subset the population using those indexes that I've sampled, the indices that I've sampled, and they produce the same values. Okay. Does that make sense there as far as sampling with indices, resampling indices rather than sampling the values themselves? Because that's how Boot is going to run. It's going to run by resampling indices rather than the values themselves. Okay, let me go ahead and give you your first view quiz answer for Friday. First view quiz answer is the letter E. E as in elephant. E as in elephant is the first view quiz answer. All right, let's take a look at an example here. For this example, I'm going to use the IRIS data set. The IRIS data set is a very popular data set. I don't know if you guys have already encountered this, but if you're going to do any kind of statistics work, at some point you're going to encounter the IRIS data set. The other popular data set is the Titanic data set. I don't know whether there's like certain data sets that constantly keep popping up in different contexts and stuff, but the IRIS data set I see very frequently. Okay, basically it's got 150 observations. There are 4 numeric predictor variables: the sepal length, the sepal width, the petal length, and the petal width. And we have 1 categorical variable with 3 categories or species that can be predicted. We have the and so it's iris flowers, and we're looking at the species Setosa, versicolor, and virginica. Okay, and it's very popular because it's very kind of clean, and there's not a whole lot of like messiness to it, and so it any kind of classification algorithm stuff works very well on this data. All right, and so Ronald Fisher, kind of the grandfather of so many of our statistical methods today. You know, we have the Fisher exact test and the F distribution are named after him and things like that. Use this iris flower data set in a 1936 paper on linear discriminant analysis, and it's kind of been a staple in statistical analysis since then. And so in my 102B class, I use the iris data set quite a bit. And if you do any kind of, if you search machine learning stuff online, any kind of classification thing, almost surely they will be dealing with the iris data set as well. Okay. And so just so you know what sepal length and what sepals and petals are, this is the flower anatomy here. Okay, and so you have the petals, and these things down here are the sepals, and then you have, you know, other stuff. Okay, and as far as the iris flower goes, okay, this is kind of what an iris goes. And so the iris, these big things which look like petals, those are actually the sepals. Okay, and then the little things in here, those are your petals. Okay, these are these standard petals, and the things that fall, those are known as the sepal. Okay, so the sepals are sometimes called falls, and they kind of like say, you know, you look at iris. Let's see if we got Setosa irises. Okay, I don't know. Is this a Setosa? I can't tell. All right, so apparently there are like, Wikipedia iris. There are 260 to 300 species of iris, which is so so amazing to me. They're like distinct species. You know, I realize how little I know about plants and flowers and stuff, right? Because, you know, you think about like dogs, and all the different dogs you see, they're all the same species. And like you know, you can take, you know, a big dog and a little dog, and you know, they can mate and have babies and stuff, but you can't have like, you can't take two different, like these irises or whatever. Like if they're different kinds, like they're not gonna produce progeny and stuff, which seems so, well, anyway. So anyway, here, I just created some summary statistics here. Okay, and so there's 4 variables, and I calculated the mean and standard deviation of each of these variables. So I've got, you know, for the mean sepal length, standard deviation of the sepal length, sepal width, and mean and standard deviation, petal length, mean and standard deviation, petal width, mean and standard deviation. And so we have 50 observations from each of these things. Setosa has 50, versicolor has 50, and virginica has 50 observations, for a total of 150 observations in our data set. And here is a plot of, you know, a pairs plot, sepal length, sepal width, petal width, and we've colored the dots according to their species, and so some of these have a lot of overlap, but you know, the Setosa is actually quite different. Okay, if you look at some of this stuff, and anyway, let's say we just wanted to do a simple test, simple hypothesis test, and so let's say we'll just do a t-test to compare the mean sepal length of Setosa versus the mean sepal length of versicolor. Okay, and so the sepal length of Setosa, the first 50 observations are Setosa. So I'm going to take iris sepal length, and I'm going to take the first 50 observations, and so these are the sepal lengths of Setosa. And then the next 50 in the data set are versicolor, and so I'm going to just take observations 51 through 100 for sepal length, and those will be versicolor. And so I can just do t-test of this 50 vectors, length 50 vector with compare that to another vector of length 50, and we're going to compare the mean of the two groups. Yeah, that's one limitation of the t-test. The t-test is only able to compare two groups at a time. And so here, that's why I'm just selecting two species, Setosa versus versicolor. There's actually 3 species in the data set. Virginica is one of them. What kind of test would we have to use if we want to compare the means of 3 groups simultaneously? Yeah, so if you want to compare more than 2 groups simultaneously, you'd have to use something like ANOVA. One-way ANOVA will allow you to compare just 3 means. And then if you've got multiple variables that you want to check, you can do like 2-way factorial or some kind of randomized block design ANOVA or something like that. So if you want more than 2, you'd have to do ANOVA. But just for simplicity, we're going to do the t-test for the Setosa sepal length versus the versicolor sepal length. And when I do this, I get a p-value of pretty much 0. Okay, my p-value is 2 times 2 times 10 to the negative 16. So we're pretty much hitting the limits of what our computer is able to kind of say is something 0. And so, you know, if you look at your test statistic t is negative 10. You know, we're always surprised. You know, anything more than 2 standard errors away from the mean is significant. 3 standard errors away is like very significant. And here we are at like 10.5 standard errors from the mean. So yeah, our p-value is going to be pretty much something close to 0. Okay, this is how we might do something if we did Bootstrap. Okay, so with Bootstrap, what we're going to do, if we wanted to resample the values directly, I'm going to kind of create my population, because under the null hypothesis, we're saying both samples are coming from the same population. And so our Bootstrap populations, we're going to just take the first 100 values, which are all the Setosa and versicolor values, and we're going to just pull them all together into one kind of population. Because under the null hypothesis, we're saying both the Setosa values and the versicolor values are coming from the same population. And so that's what we're going to do. So our Bootstrap population is going to be the first 100 values of sepal length. Did I do that wrong? Yeah, sepal length, sorry. Okay, first 100 values of sepal length. And then I'm going to, from this population, I'm going to draw 50 values with replacement. Okay, and we're going to throw that into group A. And then I'm going to take 50 values from this Bootstrap population with replacement, and we're going to throw that into group B. We're going to calculate the mean of group A and the mean of group B, and we'll take the difference between them. Okay, and so this is, you know, what kind of values would we get? And if both samples are coming from the same population, you know, and we take a look at all of the differences, as expected, if both samples are coming from the same population, our mean ends up being something very close to 0.0002698. So, you know, if the null hypothesis were true, whenever you take 2 random samples from the same population, you would expect the difference between means to be something around 0. And indeed, we're getting something around 0 if the null hypothesis were true. Okay. The largest difference we observed was 0.552, and the smallest difference that or the most negative difference that we observed is negative 0.47. Okay, so not once did we hit something where, you know, the difference between 5.01 and 5.94 is like 0.93. So not once did we hit anything as extreme as 0.93. So that's us resampling the values directly. We can perform the resampling by resampling the indices. Okay, so this is going to yield the same results, but you'll notice the code inside here is different from resampling the values directly. Here I created my population, and then I sampled values from that population. Here, I'm going to take the values 1 through 100, okay, 1 through 100, and then I'm going to sample 100 values with replacement. And so these will be my resampled indices. So I'm sampling the indexes 1 through 100, and we're going to draw a sample of size 100. And so with these resampled indices, I subset the original iris data set, and I say I only want the rows that correspond to the resampled indices. And so that's going to form my resampled data, right? So my resampled data will be 100 randomly selected rows that were sampled from replacement here, okay? And then if I do take that, what I'm gonna then do is I'm going to take the first 50 values and just throw them into group A, and then I'm gonna throw the next 50 values and throw those into group B, okay? And then I'm gonna take the mean of group A versus the mean of group B, and I'm gonna store all of those in another vector called differences B. Okay, like kind of my secondary difference vector. And if I look at that, the result of differences B is exactly the same as the values that I got when I resampled the values directly. So even though I've changed kind of the method by resampling the indexes rather than the values directly, I'm getting the exact same results because pretty much they're effectively the same thing. It's just rather than taking the values directly, I'm saying I want to take, values, 5 and 11 and 12 and something like that. Okay. Here I just to show you, if I do all equal on the kind of the differences vector that I produced back here and the differences B vector that I produced here, indeed, all of the values are equal. So resampling the indices and subsetting will kind of yield the same results here. Okay, and so when we use the library boot and its function here, what we need to do is we need to provide a function that's going to resample indices. All right, and so we have to write a function, or I'm sorry, we're going to have to write a function that uses resampled indices, okay? Because the boot function does the resampling. It passes those resampled indices and into the function, and it expects it to return some kind of statistic, okay? So again, what we want to do is we want to calculate the difference between the mean sepal length of the 50 setosa flowers and the mean sepal length of the 50 versicolor flowers. And so this is what our function is going to look like, okay? So I'm going to write a function. I'm going to call this difference function. This difference function, if you look at its code, is almost identical to the code I have in this loop here, except this function does not perform the resampling of indices. So let me actually pull up. All right, so here is the kind of the loop that I wrote where we resampled the indices. And basically I'm taking this code in here, okay, where I resampled the indices and calculated the difference. And I'm taking that code and I'm making a function out of it, okay? So inside my function, the function takes the data and the indexes, which get passed to it, and it's going to subset the data based on the indexes, okay? So this first line here is where we did the resampling. We're not going to worry about the resampling. The resampled indexes are passed to us, and we're going to just subset our data using the indexes that get passed to us. So we take the data, we just select the rows corresponding to the indexes that get passed into the function, and that's going to form the resampled data, okay? So we have this resampled data is basically the data, in our case, iris, sampled to, subset to the indices that get passed to us, right? And then from there, I take the first 50 values. We're going to throw the first 50 values of sepal length and throw them into group A. Values 51 through 100, throw them to group B. We're going to calculate the mean of group A minus the mean of group B, and we're going to return that difference, okay? Technically, I don't need to assign it to difference and return difference. I could just say return this, but just for kind of to keep it fairly consistent here, this is what we have. Is that okay? As far as writing this difference function to calculate the difference using kind of the arguments that library boot is expecting, where you have one argument being data, which is the original data set, and then index will be basically the resampled indices. Now, we don't have to do that inside this function. Library boot, or that boot function, is going to pass the resampled indexes to us, okay? So, so the boot function will perform the resampling of indices, and we'll pass those into the function that we write. Okay, and so yeah, so when we run it, this is what how we run it, and this is what we'll get. Okay, let me go ahead and give you your next view quiz answer. The second view quiz answer for today is C. C as in cat. C as in cat is the second view quiz answer for today. Okay, so when I call boot, the data that we're going to take a look at are the first 100 rows of the iris data set. Okay, because again, we're only looking at the Setosa versus versicolor, which are in the first 100 rows of the data, and we're because again, we're only right now we're just comparing two means against each other. Okay. As far as the statistic that gets calculated, we give it the name of the function that we wrote, the diff function, the difference function that we wrote back here. And so that gets passed here. And then we're going to say do 10,000 replicates here. 10,000 replicates. All right. And we take all of the results of this boot function, and we're going to store it into something just called boot results. Okay. You can name this anything you want. All right. And again, and that's what we have. All right, any questions so far? So far, so good. Okay. All right, and again, the results are gonna just, the results of boot will just be this big list, and the list of 11 with quite a bit of structure here. Okay, question, does it have to be a data frame or can it be a vector for the data argument? The data argument can be a vector, okay? The data argument can be a vector, and it's just that when you write your function, the way you subset it, you would just get rid of this comma here. Okay, you would just do data, and then you would get rid of the comma, and then it would subset a vector, right? So obviously you'd have to structure your statistic function the way you want, and then the value that gets returned, it can be a vector of statistics, right? So here I just calculated the difference between mean A and mean group B. But if you wanted to also compare like the median of group A versus the median of group B, and maybe like the maximum value, compare maximum values and minimum values, or whatever you want, you can have it return a vector of a bunch of statistics, and the Bootstrap would do it for you. Okay. All right. So anyway, this is the results of boot. It's a big list. Okay. Probably the most key things are T0 and T. Okay, pretty much all of this other stuff is just kind of like information regarding the conditions under which boot was called. Okay, so it tells you, you told me to do 10,000 replicates, and this was the data frame that I worked with, and these are the seeds, and I don't quite know how the seed thing works and stuff, but this is just information about the results that it produced. But the thing probably of interest to us will be T0 and T. Okay, T0 is basically your test statistic if the index that you passed it will just be 1 through 100. Okay, so if you take if you pass into this function, index being just kind of not a resampled vector, but just the vector 1 through 100, then what is the value that it's going to calculate? Well, if you didn't do any kind of shuffling, sepal length 1 through 50 is going to be the mean sepal length of Setosa, and sepal length 51 through 100 will be the mean sepal length of versicolor. And when you calculate the difference between those two groups, it's going to be the difference between the mean sepal length of Setosa and the mean sepal length of versicolor, which is negative 0.93. Okay, and that's exactly what we see back here. The mean sepal length of Setosa is 5.01. The mean sepal length of versicolor is 5.94. So, it's a difference of negative 0.93. If I do this minus this value minus this value is negative 0.93. And that's basically T0 is your observed statistic or observed difference or whatever it is that you're going to be, kind of comparing against your Bootstrap thing. Okay. And so this is what we get, negative 0.93. These are the results that we get from all of the different Bootstrap samples, okay? And they're all stored inside $T, okay? And so if I ask for the summary of $T, if I take a look at the results inside $T, these results aren't exactly, they are comparable. they're comparable to kind of the results that I got when I did the Bootstrap myself, but they're not exactly so, okay? And that's because when library boot does the resampling, even though I set the seed to be 1, its randomizing process is just ever so slightly different. And so the numbers that it gets will just be a little bit different from ours, okay? And it's basically comparable to just using a different seed. And what kind of results would you get if you used a different seed? You're going to get numbers that we expect are similar, but not exactly the same, okay? All right, so anyway, from this, we could calculate some kind of empirical p-value for our hypothesis test. So, the observed difference that we got was negative 0.93, okay? And I think if you look at the summary table, if I had stored more decimal places in the summary table, it would have been like 5.006 versus 5.936. And so the difference in means is negative 0.93. Again, that is stored in boot results $T0, all right? And that's negative 0.93. And we're just gonna ask, well, how often did my Bootstrap results produce a value greater than 0.93, right? If I take the absolute value of this, how often did from randomization, did I ever get a difference as great as 0.93? And the answer is no. In 10,000 repetitions, not once do we get a result greater than 0.93, okay? And so my empirical p-value is 0. My empirical p-value is 0. And that's not surprising, because when I did the t-test back here, it says your p-value is on the order of 10 to the negative 16. So it's not impossible, right? It's not, technically it's not impossible. It's just incredibly unlikely, right? It's kind of just like if I say, take a coin, flip it 50 times, and did you get heads all 50 times? Okay, theoretically, it is not impossible to get 50 heads in a row. Okay, theoretically, it's not impossible to get 50 heads in a row, but it will probably never happen in anyone's lifetime, even if they spent their entire life flipping coins all day and all night, just because the probability of it actually happening is 0. And so the empirical probability is pretty much 0, even though it's not actually 0, right? So I think this happens in your homework, and you do some Bootstrap tests, and there's going to be an instance where your empirical p-value is 0, okay? Where when you, even after 10,000 repetitions, 100,000 repetitions, just the difference never becomes whatever it is that you observe. So the reason why people like Boot is because a lot of functions have been built to work with the results of using Boot, right? So if you take Boot and you store the results somewhere, you can take your Boot results and you can just throw it into the function plot, okay? Throw it into the function plot, and it's going to produce this plot here. One of them is going to be the histogram of t, and this is effectively a histogram of the sampling distribution of all of those mean differences, okay? So what is the difference between group A and group B if the null hypothesis were true, okay? Well, if the null hypothesis were true, meaning both group A and group B were drawn from the same population, yeah, we expect the difference to be centered around 0, and that's what we see here. We see our differences centered around 0. Sometimes we get a difference as big as 0.5, sometimes as low as negative 0.5, but most of them are like between 0.3 and negative 0.3. Very rarely do we venture out here. And so we have something that looks like the normal distribution centered at 0. And this dotted line over here, this is our observed difference of negative 0.93. Our T0 is represented by this dotted line, and we can see this dotted line is way out here, okay? So not once, our sampling distribution, if the null hypothesis were true, is centered at 0, and not once did our sampling distribution ever end up way out here at negative 0.93. So that's going to provide kind of significant evidence against the null hypothesis here, because this is what we got in our sampling, okay? Here's also just a QQ norm plot of the sampling distribution under the null hypothesis, and that's what we get under if we just do plot Boot results, okay, which is nice. Okay, and then another thing, So you can also just take, ask for a kernel density estimate of the boot results and throw that into plot. I've got my formatting wrong, so it cuts off but again, this is going to be centered at 0. It's basically this picture, just stretched out. You can also take the results of your Bootstrap and ask for confidence intervals. Okay, you can just do boot.ci, give me confidence intervals, Bootstrap confidence intervals, using my results of using boot. Okay, and so this is going to produce confidence intervals. Now, because our empirical p-value for our test data is 0, it's not actually able to produce a confidence interval. Okay, so it errors out. We get an error because our empirical p-value is 0, and so it's not able to produce any kind of confidence interval for us here. There's some more information about some of this, the Bootstrap confidence intervals at this this page that you can read about there. Okay, so let me just show you another example where I do produce Bootstrap confidence intervals. Okay, and so so let's say we wanted to calculate the correlation between sepal length and sepal width. Okay, sepal length and sepal width. And if you calculate the correlation, you get negative 0.117. This is actually kind of interesting. So here is, so this is the sepal length versus sepal width. Okay, and we asked, is there correlation between sepal length and sepal width? And this is a good an example of Simpson's paradox. You guys learned about Simpson's paradox? So in Simpson's paradox, if you look at each species individually, so if you look at the red, which is Setosa, there's definitely positive correlation between sepal length and sepal width. If you look at the green species, there's positive correlation between sepal length and sepal width. Even the blue species, which probably has the weakest correlation between sepal length and sepal width, I would say there's a positive correlation, which is kind of what we would expect. You expect kind of your bigger, the bigger sepals, which again are the kind of the, not the little petals inside, but the bigger things out here, the sepals, you'd expect kind of the longer ones to be a little bit wider and things like that. You'd expect positive correlation. But when you look at all three of them together, overall, there's negative correlation if you look at all three together. And so anyway, this isn't an exploration of that. We're just doing an example just to kind of show you how this works. But anyway, so if you calculate the correlation between sepal length and sepal width, you get a negative correlation statistic. Okay, and anyway, we want to do some Bootstrap with this. Okay, and so we have to write a function to calculate the correlation. All right, and so to calculate the correlation, I'm going to take my data, which is going to be the iris data. We're going to subset it based on the indices. So we're going to take data, subset it on the indices. I'm going to store that inside resample data. And then the value that we're going to return is going to be resampled data first column, which is sepal length. What's the correlation between the resampled data first column and resampled data second column? First column is sepal length, second column is sepal width, and calculate the correlation. That's the statistic that gets returned. And so this is the function. It's very simple. And then we just say, all right, run boot on the iris data set, run correlation, 10,000 replicates. You know, store all of those, all of the values that you get back in boot results. Okay, again, boot results, T0 is what you would get if you just passed the entire length of vectors. And so this, in this case, iris is length 150. So if you passed indices 1 through 150 here, it doesn't do any kind of subsetting. And then, you know, the value that gets calculated is just the correlation, negative 0.1175, which gets rounded off for whatever reason, at least when it gets printed out here to negative 0.118 here. And then these are just the different correlations that it calculates. And so, you know, it's centered, you know, very close to the correlation that we observed in our null hypothesis here, or not null hypothesis. If we're assuming the null hypothesis, there's not actually no real hypothesis test here. We're just kind of getting an estimate of what the population value could be. But here we're assuming our data is representative of the population. And if that's representative of the population, we would expect all of our statistics to be centered quite around our kind of our base value of negative 0.118, which seems to be the case. And here, this time I can ask, all right, give me some confidence interval values. So I have boot.ci using the boot results, and it produces 4 confidence intervals, okay? 4 confidence intervals. And all of these values are kind of similar. These are all confidence intervals for what the population correlation could be based on some of our estimated sampling distribution here, right? So our correlation, if we took the correlation between sepal length and sepal width here, we're getting negative 0.117, negative 0.117, negative 0.117, something close to 0. And it turns out if we calculate confidence intervals for the population correlation, yeah, 0 is a possible value, okay? And so we have 4 confidence intervals. They're all very similar, just ever so slightly different, okay? And so just a brief explanation. The normal confidence interval, this one, uses the normal distribution, okay? So basically, for 95% confidence interval, it's using 1.96 times the standard error, and it's estimating the standard error based on the Bootstrap results, okay? So based on your Bootstrap results for the different values of correlation you're getting, it's estimating the standard error there, and it's using 1.96, okay? The percentile confidence interval takes basically all of the values that you get inside $$t, it arranges them from least to greatest, and it's going to give you back the 2.5 quantile or percentile and the 97.5 percentile. So in our case, we have 10,000 values. So it ranks them from least to greatest, and it's going to give me the 250th value and the 9,750th value, okay? Because those are going to correspond to the 2.5 and 97.5 percentile, okay? Assuming we're doing a 95% confidence level. Now you can, of course, change that to something else if you want, but that's what we would get, okay? The basic confidence interval is kind of like the percentile confidence interval, except it's not using the values t directly, but it's based on a difference between t0 and the Bootstrap replicate. Okay, so each Bootstrap replication, it takes a difference between those, and it reports percentiles based off of that. The BCA is the bias corrected accelerated interval. I actually don't know much about this one, but you can look up the documentation, and it cites Brad Efron here, and you can look up kind of the corresponding journal article from, I guess, 1996 that talks about the BCA interval, which comes up in the if you look up the help. So if you look at the help for the non-parametric Bootstrap confidence intervals, I guess the 1987 paper from B. Efron talks about better Bootstrap confidence intervals, but I haven't bothered. I haven't read that paper, so I don't know the details of it, but apparently it's better. So that's that. Okay, that's all I've got for you guys today. So let me give you your last view quiz answer. Last view quiz answer is B. B as in, I guess, Bootstrap, and that's it. That's it for today. Have a good weekend, you guys, and we will see you on Monday. So have a good night.